Is that sufficient?
Yeah.
Okay.
And what's how did you give the 5 and 10, the radius?
The 5 and 10, that's the length of the moment arm. Using this, the magnitude of the torque is RF sine theta. This is the magnitude of the moment arm times the magnitude of the force times the sine of the angle. So magnitude of the moment arm, the distance basically from the axis to where the force is applied, times the force times the sine of the angle.
The question gives us the 5 and 10?
The ladder's 10 meters long, and I'm assuming, so that's how we got the 10. And the 5 is, I'm assuming that the center of mass is at the middle of the ladder. So whatever half the length is. All right, so let's talk about the lab a little bit, because you do have that one that's at an angle. Now, I wanted the angle more than 20 degrees. I know that doesn't always happen because 20 degrees is steeper than people think. So what I didn't want is it for it just to be, a slight inconvenience off the horizontal. I wanted more than it looked like, oh, they just didn't bother leveling it. So 20 degrees is suggested just so that you get it at a decent angle. In other words, if it turns out not 20 degrees or more, relax. Now, the moment arm, if you have, I guess, a force acting this way, a force acting that way, and then you get various things hanging on it. We'll just take these as a start. Officially, the length of the moment arm is that right there. But on the table, I didn't really give you a place to put the angle. The original intent, when I wrote that, was that if we think of the magnitude of the torque as RF sine theta, that really is what I was thinking of as the moment arm when filling out the lab. I probably should adjust it so that I throw an angle in there. In other words, you're finding, in essence, should not be using the same letter there. Oh, 5. This distance right here, the horizontal distance from the moment arm to where the force is applied. That was my original thinking when I wrote that lab. Somehow you need to take the angle between the two vectors, between our moment arm and our force. Somehow you need to take that into account. So I will accept either you take the angle into account when you report the moment arm, and I'll know it. I know what the position is. I know what the moment arm. I can easily figure out what the horizontal length is, and I can figure out what the angle is. Or go ahead and put down this distance right here as R. But when you figure out the torque, you need to take the angle into account at that point. So either take the angle into account when you record what the moment arm is, or when you calculate the torque. Either way, but you got to take the angle into account somewhere. Other questions right now?
Yeah, so that's how to find the moment arm for the one with the angle, which is D. But for E, what would you want us to do for the moment arm?
That's because E was horizontal again.
Okay, so it's the same. Okay, so
E would be the same as the other
C.
as B and C. Other questions right now? All right. Enough with equilibrium. We need some lack of equilibrium. We're now going to remove one of our ideals for the rope. There is now friction between rope and pulley. Classic physics approach, you start with a nice ideal situation and then you just slowly start adding reality as we go. This has mass to it, so we now care about that. So let's make, so this is some radius and some mass, some P for pulley. Let's make this 5 kilograms. Make this 8 kilograms. And make this 3 kilograms. And we'll make the radius 0.4 meters. It's a big pulley. Yeah, so the diameter, the pulley has a diameter like that. Acceleration of masses. That's what we're trying to find. The pulley is being suspended. This is not like, it's not like I have a pulley and 2 masses and a rope there and suddenly the thing's in free fall. Now the pulley's being held up. And I am still keeping that assumption that it is frictionless right here. Bearing at center, wasn't quite sure what to call it there, but there's no friction right there in the middle. I am going to still add one bit of ideal. Rope does not slip. In other words, the friction between the pulley and the rope is static. And now we will go through the exact same process that we have done so many times before. So we got mass 1, pulley, rope, mass 2, and we'll throw the ground into it. Let's do the whole bit. Now, even though it is a single rope, the tension in the rope is not the same on both sides. Because if I start this thing out and the pulley starts at rest and the pulley starts turning, there has to be a net torque on it. It's the rope that's causing it to turn. If I had the same tension on both sides of the rope there,
it wouldn't turn.
right, because the torque would be 0 and it's starting at rest. So the tension here and the tension here are not the same.
Well, there's no friction. The tension, we can just label it differently, like FT1 and FT2, so.
All right, so I've got FT1, 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 FT1.
And then FT2 for mass 2, or the rope.
Is there a normal force the rope have to get on the pulley?
I am considering the part of the pulley, since I'm sort of treating these as separate, the part of the rope that's touching the pulley right here, I'm not worrying about, it's part of the pulley. Because I also really don't care what the friction is between the rope and pulley, just so long as I know the rope's not slipping.
There's a weight on the pulley and the two masses.
All right, so I got W sub 1, W sub 1, W sub 2, W sub 2, and W sub P, W sub P.
You said there was friction between the rope and the pulley, right?
There is, but as long as it's static friction, I
They
don't
don't,
care.
okay. Would that mean there's a normal force on the rope between the rope and the pulley, or do we just say that it's not existent?
Not worried about that.
Okay.
Yes, there is, but I'm treating the rope as sort of three different things. I got the left side, the right side, and then the part of the rope that's in the middle, I'm just treating as like part of the pulley. It's still a massless rope.
Okay.
So in that case, the friction force there would be considered the internal force, since that part of the rope and the pulley I'm treating as one object.
Okay.
There is one other force here, that at least, even though it's not gonna play a role in our solution, is something that I would at least like to acknowledge.
Is there a norm or an other force?
Where,
I have no idea.
Does it have to do with the radius of the pulley?
Oh, is it the bearing?
yeah, the bearing is what I was going for. And that would be there regardless of what the radius is, as long as the radius is not 0. Yet the pulley's being held up by something. The way it's looking right here, this thing's in, not only in free fall, this thing's worse than free fall, this thing's being dragged down. So there's a force acting up. I'll just call it Y. There's only one normal force here that we're worried about. All right, so I got things moving in multiple directions. Which way is this thing gonna go anyway?
The 8 kilogram mass is gonna accelerate towards the ground.
Okay, so that's gonna accelerate that way. Which way is the mass 1 gonna go?
It's gonna accelerate that.
Which way is the pulley gonna go?
It's gonna stay static.
Oh, I hope not.
It'll be like in the,
Is this
it'll
three-dimensional?
have rotation in the direction of the movement, I guess, or,
Or into the board.
yeah, into the wood.
All right, so, and I put an alpha there because it has angular acceleration. The center of mass is not moving at all. The center of mass has an acceleration of 0, but the pulley itself will be rotating clockwise some points into the board. I have 3 different objects here. I don't have to have the exact same convention for all of them. It's really nice when it works out that way, but we don't have to do it since they basically have accelerations in 3 different directions. Or 2 accelerations and an angular acceleration. So for this one, I would suggest up is positive. For this one, I would suggest down is positive, and for the pulley, I would say into the board is positive. I will have 3 equations. Well, 3 equations of motion, I should say. We will have 4 unknowns, so we'll have to get another equation from somewhere.
We don't really have a J hat here, do we? Well, what's I hat, what's J hat?
All right, because each of these is moving in one dimension, I can get away with just plus or minus. But if you want, we can make that J hat 1, J hat 2, and
Okay, yeah.
There we go.
Okay.
So I have a J1 hat, a J2 hat, and a K hat. Those are my three equations of motion. Somebody give me one of them.
FT1 minus, weight 1, or is that, yeah, is equal to mass times acceleration?
You can do better.
Huh?
Be more specific.
Mass times acceleration due to gravity?
No.
Mass 1 times acceleration?
Mass 1 times, okay.
All right. Second equation?
Force of tension 2, minus weight 2 is equal to mass 2 acceleration. Are the accelerations gonna be the same? Yeah, they should be, because it's an ideal rope, right?
Almost ideal. There's friction there between the rope and the pulley, but we're assuming it's still not stretching. What's wrong with this equation here?
We
Yeah.
may flip this up.
Yeah.
Oh, yeah, because we made down positive, okay.
If you made up positive, then this part would be right, but this is the magnitude of my acceleration, and so I'd have to stick a negative sign here if we made up positive. So, now we're good.
It's the magnitude of your acceleration, you said?
A is the magnitude of my acceleration.
Oh, yeah, okay.
All right, and now the K hat equation. I have 4 forces acting on the pulley there.
Only 2 of them are rotating it, right? Or applying torque?
Okay? So, we have a natural axis of rotation. So the weight of the pulley and the normal force exert absolutely no torque. So which is exerting positive torque?
FT1?
FT2.
FT2, because that's moving counterclockwise, and we defined into the board as positive.
Yeah. FT2 is one that's.
Right.
The moment arm is that vector right there for FT2, so this is, I guess, R2. What is the angle between them?
90 degrees.
Okay, either one. And so my torque is just the magnitude of sine. Sine of 90 degrees is 1. It's just the magnitude of R times the magnitude of the tension. I'll just write it as R FT2 minus
FT1?
R times FT1.
there we go, R FT1 equals
MP, right?
no.
Yeah, alpha 1.
This is a rotation equation. I've written it up a couple times. We haven't done a whole lot of detail on it, but there
It's,
is,
I alpha?
Oh, right.
yep, I alpha. Now, I will tell you I am gonna make the assumption that this is a disk. And the formula for I for a disk is 1/2 mr squared. You know what, I probably should stick to a convention here, so mr squared. It's the mass of the disk and the radius of the disk. Why I capitalized it, hopefully I will explain when we talk about I in more detail.
What is I?
It's the moment of inertia.
Okay, yeah.
It's an indication of, the higher the moment of inertia is, the harder it is to get it to either start rotating or stop rotating, whichever one it's.
And the moment of inertia is the equivalent to our linear velocity. What is it? It's like
It's the analog of mass.
mass, okay.
All right, so substitution next. So I have FT1 minus M1G is equal to M1A. I have M2G minus FT2 is equal to M2A. And down here, RFT2 minus RFT1 is equal to 1/2, I guess, mass of pulley times radius times alpha. R squared. Now, M1G, M2G, the masses we know, R we know. Not gonna make substitutions for, I'm not gonna plug numbers in quite yet. But we know our unknowns are tension, 1, tension 2, acceleration, and angular acceleration. And I have 3 equations for unknowns. So I need to somehow relate, I need another equation somewhere. So I have a disk that's spinning. What is the relationship between the linear speed of, let's say, a point on the edge here, the relationship between the linear speed of that point and the angular speed?
Are they the same?
They wouldn't have the same units, can't be the same. We first discussed this relationship when we did some typical acceleration. We'll do it before then. I did that whole spiel with the Babylonians.
Does that have to?
What's the relationship between, can you repeat what you said just a second ago?
What is the ultimately, in order to get the relationship between A and alpha, I'm asking for the relationship between speed and linear speed and angular speed.
Does it have the same magnitude, just in radians?
I'm not quite sure how that would work.
It has something to do with radians though, because of the Babylonians, right?
Yeah, it has something to do with it.
Okay.
Or the relationship between arc length and angle.
Is it 2 pi r? No, arc length is equal to, so to find the angle, you have to do 2 pi r, right?
Depends on what you do with it.
That gives us the arc length, right?
That would, depends on how you're doing it.